In the last part of this measurement concepts module, we'll take a look again at the normal distribution and how to use it for common measurement problems. Then we'll move on to finite statistics, where sampling prevails, and we'll learn how to use the student's t-distribution. The normal distribution parameters mean and standard deviation are associated with the probability of a population. The area under the portion of the probability density curve Px, defined by the interval x prime minus z1 sigma is less than or equal to x is less than or equal to x prime plus z1 sigma, gives the probability that a measurement will assume a value within the interval. Direct integration of p for a normal distribution between the limits of x prime plus and minus z1 times sigma with z1 equal 1 covers 68.26% area under the curve p of x. This equates to 68.26% chance that a measurement of x will have a value within the interval of x prime, the mean, plus or minus 1 standard deviation. As the interval defined by z1 is increased, the probability of occurrence increases. For z1, we have 68.2% area under the curve for plus and minus 1 standard deviation. z1 of 2 gives us 95.45% area under the curve for 2 standard deviations. And z1 of 3 gives us 99.73% area under the curve for 3 standard deviations from the mean. It follows directly that the representative value that characterizes a measure of the variation in a measured data set is the standard deviation. The probability that some ith measured value of x will have a value between x prime plus and minus z1 times delta is 2 times the probability of z1 times 100, or p%. This is written as x sub I is equal to x prime, the mean, plus or minus z1 times the standard deviation at a given probability. Thus, simple statistical analysis provides useful quantification of a measured variable in terms of probability. This can turn out to be useful in engineering situations where the probable outcome of a measured variable needs to be predicted or specified. For our next manufacturing industry problem, we'll take a look at a lumber mill grading issue. A small family lumber mill historically grades wood using a normal curve. For any grade x, based on the mill's mean, x bar, and standard deviation sigma over years of testing, the following grade rules apply. There's intervals defined for A, B, C, D, and F grades with intervals using the mean and standard deviation. A bank considering a loan to the mill hypothesizes mill growth may have been constrained due to assuming an overly conservative grading system with unnecessary rejects. For due diligence, the banker would like to know how many A's and B's and C's and D's and F were graded for a given 100 boards produced. To determine the number of boards for the grade intervals defined, we have to use the normal Gaussian distribution function and the definition of the z-score. We see the key thresholds are 1.6 standard deviations from the mean and 0.4 standard deviations from the mean. These correspond to z values and probabilities that we can look up in a z table. For example, for A's, we're looking at that far right tail, shaded on the right here, and that corresponds to 0.5 probability minus the probability of 1.6. So we look up the probability of 1.6 in the table and we see that it's 0.4452. So the number of A's is just 0.5 minus 0.4452 times 100, which is about 5.5 or 5 to 6 A's. Since we don't have decimal number of boards, we count it to the nearest whole number, between 5 and 6 A's. Okay. The 0.5 comes from the normal distribution from the mean in the very middle over all the way to the tail is a total probability of 0.5, and that's symmetric on both sides. For the C's, we also are just looking at the interval in the very middle of the normal distribution curve, plus or minus 0.4. So we need to look up the probability of 0.4 from the z table, which is 0.1554. And because it's symmetric, we just multiply that by 2. That gives us a total number of c's in the middle of about 31. The d's, we just need to use a little probability density function math, which just means that we need to recognize how these areas add up, or we can find the area in one section by subtracting off the areas in another section. So we still just need the probabilities of 1.6 and 0.4, but this time we can just subtract the probability of 1.6, probability of 0.4 from 1.6. So it's 0.4452 minus 0.554 times 100, or about 30 Ds. We can do the same thing similarly for the B's and F's. With this information, the banker providing input to the mill owners might say, yeah, maybe your grading system is a little too harsh. Maybe you have too many F's and D's. Is there a way that you can consider regrading to have more positive grades so they're not all rejected, so you can still generate some profitability from this? Statistics of finite-sized data sets. We now try to predict the behavior of a population of variable x based on knowledge obtained from a finite-sized random sample of x. For example, if we recall the box of bearings discussed previously, some 24 bearings were measured, each having been randomly selected from a population numbering in the thousands. Within the constraints imposed by probability, and if we assume a probability density function for the population, it's possible to estimate the true mean and true variance of the population of all the bearings from the statistics of a small sample. The science behind using the small sample to characterize the behavior of an entire population is called inferential statistics. Suppose we examine the case where we obtain n measurements of x. Each measurement represented by x sub I, where I equals 1, 2 to n, and n is a finite value. In cases where n does not represent the total population, the statistical values calculated from such finite data sets are only estimates of the true statistics of the population of x. We refer to such statistical estimates as the finite statistics. An important point, whereas infinite statistics describe the true behavior of the population of a variable, finite statistics describe the only behavior of the sample data set, which we then use to infer the behavior of the population. Finite-sized data sets provide the statistical estimates known as sample mean, x bar, and sample variation, s squared, and its outcome, the sample standard deviation. The quantity in parentheses, xi minus x bar, is called the deviation. The sample mean value provides a probable estimate of the true mean value, x prime. The sample variance represents a probable measure of the variation found in the dataset. The degrees of freedom nu in a statistical estimate equate to the number of data points minus the number of previously determined statistical parameters used in estimating a value. For example, the degrees of freedom in the sample variance nu is equal to n minus 1, as seen in the denominator. These equations are robust and used regardless of the actual probability density function of the population. The relations between probability and statistics previously developed can be extended to datasets of finite sample size with only some small modification. When the parameters of the mean value and variance are based on a sample rather than the entire population, the z variable does not give a reliable weighting to the true probability of the population. Instead, we introduce the student's t variable. For a normal distribution of x about some sample mean value x bar, we can state that statistically xi equals x bar plus or minus t times s of x and get some probability p%, where the value t provides a coverage factor used for finite data sets in which replaces the variable z. The student's t variable is defined as t equals x bar, the sample mean, minus x prime, the true mean, divided by S of x, the sample standard deviation, divided by square root of n. The interval plus or minus t times S of x represents a precision interval given a probability p%, within which one would expect any measured value to fall. The value of the t estimator provides a coverage factor, similar to the use of the z variable that is a function of the probability p and the degrees of freedom nu equal n minus 1. These t values can be obtained from a table like this one, which tabulates the student's t distribution published by William Gossett way back in 1900s. Gossett recognized the use of the z variable did not yield accurate estimates of the percentage interval for small degrees of freedom. Careful inspection of this table shows that the t-value inflates the size of the interval required to attain a percentage probability p at small degrees of freedom. That is, it has the effect of increasing the magnitude of t times the standard deviation relative to z times the standard deviation at a desired probability. However, as the value of n increases, t approaches those values given by the z variable, just as the value of the sample standard deviation approaches the population standard deviation. The behavior of the student's t probability density function is illustrated in the figures here. We observe that the distribution is bell-shaped and symmetric, but changes in width depending on the degrees of freedom, nu. Smaller values of nu have a wider curve, with wider tails than the z variable. But the distribution narrows as it approaches the exact shape of the normal distribution for nu heading to infinity. The total area under the two-tailed curve is 1 regardless of the degrees of freedom. The figure illustrates the relationship between probability and probability density function remains related to the area under the curve, just as it is with the normal distribution. Here, for nu equals 10 and 95% probability of the area falls between minus t and plus t, with 2.5% of the area to the right of t with the degrees of freedom of 10 and 95% probability, and 2.5% to the left. We point out that for very small sample sizes, n less than 10, the calculated statistics can be quite misleading. In that situation, other information regarding the measurement may be required, including additional measurements. If we were to take a second batch of 24 of the bearings discussed previously and measure each bearing's diameter, we would expect the statistics from the new sample to differ somewhat from the first sample. This is due to the variation in each bearing's diameter arising from manufacturing tolerances, random chance. The difference between the calculated mean diameter of each batch and the mean diameter of the entire box is a random error due to using small data sets to infer the statistics of an entire population. So how can we quantify how good our estimate is of the true mean based on a sample mean? Suppose we were to take n measurements from a large population of variable x, each measurement taken under fixed operating conditions. If we were then to duplicate the procedure m times, m sets of n measurements, we would calculate slightly different values for the sample mean and the sample variance for each set. Why? The chance occurrence of events in any finite size sample affects the estimate of the sample statistics. This is easily demonstrated. From these m replications of n measurements, we can compute a set of m values. We would find that the population of the mean values would themselves be normally distributed about some central value. In fact, regardless of the shape of the probability density function p assumed, the distribution of mean values obtained from all possible random samples will follow a normal distribution. This process is visualized in the following figure. The amount of variation possible in the sample means would depend on two values, the sample variance, Sx squared, and the sample size n. The discrepancy tends to increase with variance and decrease with n, the sample size, to the square root. The variation in the sample statistics gathered from each data set is characterized by a normal distribution of the sample mean values about the true mean. The variation is estimated from a single finite data set using the standard deviation of the means, S sub x bar. S sub x bar equals the standard deviation over square root of n. This statistic is also known as the standard error, or the standard error of the mean. The standard deviation of the means provides a measure of how well a measured mean value from a small sample size represents the true mean of the entire population. The range over which the possible values of the true mean might lie at some probability p based on the information from the sample data is given as x bar equals plus or minus students t times the standard error, where plus or minus t times the standard error expresses a confidence interval about the mean value. The coverage factor t at the assigned probability p within which one would expect the true value x to fall. This confidence interval is a quantified measure of the random error in the estimate of the true value of the variable x. The value s sub x bar, the standard error, represents the random standard uncertainty in the mean value, and the value of t times the standard error represents the random uncertainty in the mean value at p% confidence due to variation in the measured data set. In the absence of systematic error in a measurement, the confidence interval assigns the true value within a likely range about the sample mean, one due solely on the sample size. The estimate of the true mean value based on the statistics of a finite data set is then stated as the true mean x prime equals the sample mean x bar plus or minus t, students t, times s sub x bar, the standard error. This is one of the most important and powerful equations in engineering measurements. Let's consider a process control example. From 19 sampled measurements of a pressure-controlled microscopic particle deposition process, the mean operating pressure is 4.97 kilopascals, with a standard deviation of 0.461 kilopascals. A quality assurance engineer would like to know, 1, if more measurements are taken, estimate the expected range of pressure for 95% of the measurements, and 2, neglecting other sources of error, can we state the population true mean pressure at 95% confidence? For this process control manufacturing problem, the first thing we're going to do is identify that there's a finite number of samples. So this is a sample problem that we're going to assume a student's t distribution. We have the sample mean, 4.97 kilopascals, and the sample standard deviation, 0.461 kilopascals. We also have the number of samples, 19. What we're looking for is an answer to the question that if more measurements are taken, what's the estimated range of 95% of the measurements? So we look up the student's t using the degrees of freedom n minus 1, or 19 minus 1 equals 18, with a probability of 95%. That coverage factor t is 2.101. That gives us a range of 4.873 to 5.067 kilopascals for 95% probability, the answer to our question. The second problem is very simple, but we should be pretty clear about what it's asking as distinct from the previous problem. Here, we're asked to find the population true mean pressure at 95% confidence, which is another way of saying what's the confidence interval at 95% confidence. So in this case, we're going to use the standard error, S sub x bar, which is the standard deviation divided by the square root of n. So our true mean, x prime, is the sample mean, x bar, plus or minus students t times the standard error. We look up the students t of 2.101, same as before. And this time we multiply times the standard error, which is the standard deviation over square root of 19. With this, the population true mean confidence interval at 95% probability is between 4.948 and 4.992 kilopascals. Here we see the student's t table for 18 degrees of freedom. At 95% probability, we see a t of 2.101. For our last industry example, we'll look at rivet strength. A batch of rivets is tested for shear strength. A sample of 31 rivets shows a mean strength of 924.2 megapascals with a standard deviation of 18 megapascals. An aeronautical engineer is required to estimate the mean shear strength for the batch at 95% probability. To estimate the mean shear strength for the batch of rivets at 95% probability, first we recognize that we have a sample, so we have a finite data set. We can assume a student's t distribution. The sample size is 31 and the sample mean is 924.2. The sample standard deviation is 18. So our shear strength, x bar minus x prime over sx over square root of n, that's what we're looking for. Our degrees of freedom is n minus 1, which is 31 minus 1, or 30. We use table 4.4 to look up our student's t for 30 and 95% probability, and our student's t coverage factor is 2.042. So our standard error, S sub x bar, is our standard deviation divided by square root of n, 18 divided by square root of 31. And then our true mean is our sample mean plus or minus our student's t times our standard error, 924.2 plus or minus 2.042 times 18 divided by square root of 31. That gives us a true mean value of 924.2 plus or minus 6.6 megapascals at 95% probability. That's our 95% confidence interval, or stated as a range, 917.6 to 930.8 megapascals is the mean shear strength for this batch of rivets.